So we're going to explore the perpendicular bisector idea and connect.
That's harassment or something, right? Assault?
We're going to connect a vertex on the pre-image to its corresponding vertex in the image and define the relationship between those. That's the idea. So first, you have an opening exercise to do on that page. And what you need to do, with your partner, person you're working with, is use your compass to construct a perpendicular bisector for the segment that's drawn on page 96. Go ahead and do that. So your construction should look like this, and let's see what you have filled in on your blanks over here. So Brendan, what did you guys get for the first blank? Two lines are perpendicular if they what? Brendan?
I got you.
So Sarah, what did you get for the first one?
Intersect.
Intersect. Yeah. And then how about the second one, Brendan? You think you got that one? If any of the angles formed by the intersection of the lines is a right angle, and then the last one, or 90 degrees is fine too. And then the last one here, two segments are perpendicular if the lines containing them are perpendicular.
Wow.
That's smart you are.
Thank you, Mr. Randall. You know what, Dylan?
Yeah, me, Dylan.
So we need to kind of go back and discuss perpendicular bisectors in depth a little bit more. We used them in lesson 14 when we talked about lines of reflection. Remember that? When we reflected an image, then we created perpendicular bisectors and said the distance from the pre-image to the perpendicular bisector and the image to the perpendicular bisector of the corresponding vertices must be equal to each other.
Oh.
So we figured out where the line of reflection was, then you could draw segments that go from the vertices to the line of reflection and then cast them across the line of reflection. Yes, sir.
Instead of doing all that circles and crap to figure out the line of reflection, couldn't you just continue the lines and where they connect with the line of reflection?
So if you take this segment at the bottom of the triangle,
No, the other, the top.
if I take this here,
No. That one and then that.
this one down,
No, no. The other one. The one going towards it. Yeah, there you go. And keep going. And then do the same with the other one. And then that's the dot.
no, I agree with you that that would be on the bisector, but I still don't know like at what angle exactly that bisector is.
Well, figure out what angle that is and then just cut it in half.
Cutting it in half isn't going to solve my problem there. That's why when we actually do this, Sarah, remember, we would construct segments together there, find the perpendicular bisector of these two segments, and we discover that they're the same. That's how we find our line of reflection. Remember doing that?
I do.
Yeah. Okay. So the next question here is it possible to find or to construct a line of reflection that is not a perpendicular bisector of a segment containing a point on the pre-image to its image?
No.
So we would have to say yes? Okay, so how would you do that?
I think the thing to say is no.
No, you can't.
Because you wouldn't ask it if you could.
Just draw your
That's
little
not true.
line, take your little compass and you use a circle.
So hold on. Rayanne, what did you say? If it's what?
If it's reflecting, then it's part from the bisector.
Okay, so if we have a line of reflection, by definition, the distance from one vertex to the line of reflection needs to be the same as the distance from the other corresponding vertex to the line of reflection. And the only way to get a line of reflection then is to have a perpendicular bisector, or to use a perpendicular bisector to discover where it is. So it's all based on the definition of a perpendicular bisector. Do you remember the little letter that we used for a reflection?
R.
Upside down V.
It is an upside down V.
Which? Oh.
Okay,
Oh,
which?
rotation was an R?
Yep. which is actually the Greek letter
A.
I thought you were gonna.
lambda. I'm not, but it's such an opportunity to learn Greek. Who doesn't want to learn Greek?
I know, I do.
All right,
Do you know how to speak Greek?
lambda, just biblical Greek.
Huh?
Biblical Greek, not classical. I can't speak current Greek, just old Greek. And just a little bit because I took 2 years. Okay,
Oh, I didn't
so that's
know.
lambda. Latin, that was a far better language to learn.
I wanted to learn Latin.
2 years of that in high school. Okay, so it didn't work because the definition of a reflection is something that is the same distance away from the line of reflection as Rayan already mentioned. It's about the definition of it. So let's think about the problem from a different perspective. We determined that any point on the pre-image is the same distance from the line of reflection as its image. Therefore, the 2 points are equidistant from the point at which the line of reflection intersects the segment. So what that means is, if I've got 2 triangles, I'm reflecting it across the line. There are 2 triangles there. I can say, we'll call this point R. This would be my R prime, right? I'm reflecting it across. R prime and R are the same distance from L. That's what equidistant means, right? So if I were to draw the little segment thing, this would be congruent. So what if, instead of placing this point M here, what if we placed like the point over here and called it N? Would R prime to N and N to R be the same distance? Yes. Why is
Anything
that?
on that line would be the same distance.
So does it matter where I place my point on the line of reflection when I'm comparing that? And does it matter which vertex I pick in the pre-image and the image to correspond? Whoa. Okay. Well, the things you're discovering now. So you pretty much already did example 2 without even really going through it at all. So that's what we're doing here. GP and pH are congruent. Do you agree?
Yes.
All right. Okay. Does anyone know why or how you would prove that? Or how you would come up with a scenario where you could prove it?
Circle.
Actually, not a circle. It doesn't have to do with circles, Sadie. Here's what it has to do with. What did I just create?
A triangle.
Triangles. So what you're going to discover next week, we're going to start connecting this to triangles because there are certain triangles that are congruent to one another. Another weekend.
Oh, yeah, because next week is Thanksgiving.
Tuesday. We'll talk about it on Friday. Okay. So, yes, I agree with you. They're congruent. It doesn't matter where I place point P on the line of reflection. It doesn't matter which vertex I pick in the pre-image and the image, as long as they correspond. Like, I can't use that and call it L, and then use this one and call it M, and use L and M, because they don't correspond to one another in the image and the pre-image, right? So if I pick L here, where do I have to place M? At the corresponding vertex in the image. Yes? Okay. So we explored perpendicular bisectors as they relate to reflections, determined that they're essential. Are perpendicular lines, or perpendicular bisectors, essential to the other 2 types of rigid motions? Do I need to use perpendicular bisectors when I'm rotating?
Yeah.
Like, rotations were the first ones that we did, so it might not be fresh in your mind. So thumbs up if you think yes, thumbs down if you think
Wait, if we need to use
no.
what?
Perpendicular bisectors. Do you use perpendicular bisectors when you're performing a rotation? Okay, that's what I thought. Some of you are kind of cloudy on that. So we're going to talk about that in just a second.
Yay.
How about translations? Those are ones we did yesterday.
Yeah.
So when we're doing translations, do we need to know or do we need to use a perpendicular bisector when we perform a translation? Remember how we did that? We would have like some kind of quadrilateral thing, and we would, or that's not a quadrilateral, but some kind of 5-sided polygon. And if we translated it, how did we do that? We used something called a vector, right? And then all of the vertices would be, what do we have to do with those? We would have to draw parallel lines, right, going through each vertex that was parallel to the vector, as you can see mine clearly are, and then we would figure out how long the vector was and apply it to each one. I would use my line tool, but I'm not right now.
It looks better when you do.
Okay. See, what I want to be able to do is like pick this thing and then highlight all this and then put it on like the Smart Shape tool. You know, the one that like makes it perfect. That's what I want to be able to do. So now, see, it doesn't do it for me automatically, so I have to like go back. And then
Oh, you just use that all the time.
I just forget.
It's like perfect. It's way more easy.
Anyway, that's how you would do that, right? If we wanted a vector that looked like this.
Honestly, your arrow looks like, oh.
It doesn't make a smart arrow. It's okay.
Maybe if you finish it, yeah. Finish the line.
Okay, well, this has been fun.
Oh, that's right.
Okay.
That's getting better.
Okay, whatever.
Close enough.
Okay, so for example 3, you need to find the center of rotation in this figure. To do that, I will give you a little hint. If you forgot how to find the center of rotation, find it on page 73 in your booklet and read the directions to do that with your partner, and you have 4 minutes and then we're going to wrap this up. What did you come up with for A prime, B prime?
Who?
You, Dakota. Are they the same length?
Yeah.
These two?
Yeah.
Why? Because you have to justify your response, right?
Yeah.
Okay, so if I have AB here, and I have A prime, B prime, why are those two congruent? It's just a rotation, so because it's just a rotation, so since it's a rotation, what?
Isn't there another? Oh, that's the diamond.
Yeah, that's the one that's not rigid. What does rigid mean anyway?
Like,
Fixed.
bumpy?
Fixed. Not flexible, not stretchy.
That's what rigid means?
Fixed.
Oh,
Rigid
I thought
motion.
it means like a bumpy.
It also means that. That's two meanings. But rigid also means fixed, so you're not going to make it larger or smaller. It's not going to expand or contract. It's going to remain.
What is that one? You know, like, when you know, there's like rotation, reflection, translation, and then there's the one.
Dilation. So, since it is a rotation, what do you know about all the segment lengths? The segments remain
You know what I mean?
What?
at a constant length.
What was it saying?
Okay, now why is A prime equal to B prime? So where's A prime? This segment here. Why is that the same as B to B?
What is the
Or
word
is
for
it?
segment?
Does A prime have to be equal to B prime?
Yes? No.
Yes or no? So yes, it is a rotation, so what does that tell you?
That it's not going to change. They're always going to be.
Aaron?
B prime is not always.
So how did you figure that out? Okay, so if we draw some segments here from B to B prime and A to A prime, let's find out if those are congruent in length. So if I take this segment, move it out here, segment, move it out here, I could take this one and like rotate it, right? What do you notice about them? They're not the same length. They look very close, but they're not the same necessarily in every figure. In fact, if you look back at, well, I guess that was a reflection. Okay. So they're not the same necessarily. But you know that AB and A prime and B prime definitely are the same because that has to do with the definition of what a translation or a reflection or a rotation is. Okay. There are 4 exercises that you need to do, and for each one, there are three parts. Well, it's like this whole page disappeared. For each one, there are three parts. You need to first identify the kind of transformation that is taking place. So your options are reflection, rotation, and translation, right? Then you need to determine whether or not you need perpendicular bisectors to accomplish the transformation. And if you do, you have to draw them in. And then lastly, you need to give an example of distance preservation. So for example, on number 1, distance preservation would be that the distance from A to my line of reflection is the same as the distance from A prime to my line of reflection, if it were a reflection, which this one isn't. Right. Okay. So, work with your partner on that. I would give you about maybe 3 or 4 minutes on each one, and then I'll show you what the answers are. Okay.
Oh, yeah.
Wait a second, almost.
Almost?
Make
Okay.
it automatic.
So, for number 2, what kind of a transformation is that? Colton, what'd you get for number 2 for your transformation? Sorry, we can't hear you because people are talking.
It's a translation.
We're
Sarah.
talking about VR.
So number 2 would be a translation. And then, do you need perpendicular bisectors when you're making a translation? No, because it's parallel lines, so they're not necessary. How do you preserve distance? Well, AD and A prime D prime are the same because the rigid motions. And then DC and D prime C prime are the same as well. Okay, are you ready for 3 or are you still working on 3? Okay, still working on 3.
Oh.